Okay, now we're talking about equilibrium constant and the reaction quotient. So the reaction quotient Q is, so reaction quotient, ooh, is the relationship of the activities of the products divided by the activities of the reactants. You've seen all this before, and I don't mind saying that because I know you have. If you've got A plus B is in equilibrium with C plus D, I know you've done this with Deanna. Then the equilibrium constant is going to be defined as C, concentration of C, concentration of D divided by concentration of A, concentration of B. Cool. That's not completely correct. That is an approximation. Oops, that should be an approximation symbol. So where you've got products over reactants, their concentrations. This is an approximation because it's taking into account that their activity coefficients are equal to 1. So let's talk about activity coefficients real quick. And activity coefficients are from section 5F. So I'm jumping back a little bit into section 5 to talk about activities. So this is from 5F, or 5F, there we go. Activities. Yay. Okay, so recall that mu is equal to mu star, standard conditions, plus RT log PA over PA star. I lied, that was star. Okay, where this is the chemical potential of pure A. And likewise, this is the vapor pressure of pure A. Star means pure. Okay, so what we're going to do is we're going to define activity A of A is equal to PA over PA star. But wait, you might think, well, wait a minute, isn't PA over PA star the same as the mole fraction? And this is Raoult's law. I never spell Raoult's right. Raoult, O-U-L-T-S law. You are correct. This is a limiting law that the Raoult's law says that the relationship or the ratio of the vapor pressure of A to the vapor pressure of pure A, not in the mixture, is going to go to the mole fraction of A in the limit as the activity goes to the mole fraction. Let me say that again. Okay, so this is true. I'll come up here. So as the activity of A becomes the mole fraction of A, the mole fraction of A goes to 1. Okay, so this is, as this becomes more true, you have more pure A, this becomes more true. Okay, it's a limiting law. And so, or sorry, this is the limiting law. Forgive me. So as you have more and more pure A, the activity becomes the mole fraction. So this is a limiting law that it needs to be almost pure A in order for this to be true. All right. And so the way that we relate this to concentrations is, so this would be for mixtures of two liquids together, because again, these are all in terms of their vapor pressures. For non-mixtures, so for a solute and a solvent, you've got the activity of A is equal to the activity coefficient times the concentration of A. Okay, so this is called the activity coefficient. And this is just the concentration of A. All right. So A, the activity of A goes to the concentration of A for the activity coefficient equal 1. So as the activity coefficient gets closer and closer to 1, this becomes more true. Go team. You must be like, what the hell, Allison? This is ridiculous. Why are all these extra components and stuff? We have chemical character. Molecules have identity. As they start to have identity, they're not going to behave in this really nice, simple, you always have the concentrations are representative of your system. We have to start to take into account the fact that not all chemicals are going to act the same way. And the way we do that is with empirical parameters. And the activity coefficient, this guy right here, is one of those empirical parameters that we use. This is all determined experimentally. There is no way to predict what the activities will be. We're getting pretty good at it, but we still don't have a direct way. So for, let's say you've got, the activity coefficient is 0.85. Okay, so this means essentially 85% of A are active in establishing, oh my gosh, C. Can't write sideways. So 85% of A are active in establishing where we are with respect to the reaction quotient, which is where we are along this curve. If I have, say, maybe not. So here's my kombucha, yay. If there was a chunk of solid at the bottom here, I'm trying to think of something I can throw in. Why not? Okay, so I just threw in a Lego into my tea. The Lego itself, only the outside of it is going to be possibly interacting with the tea. The inside of it, there's no way it's going to get, those molecules aren't going to get to the outside of the tea. Now, granted, this is an extreme case because that's a solid in the liquid. But if that was a single molecule, it would then be active in the solution because it would be completely dissociated. So we have my Lego in the liquid. So all of this stuff on the surface is going to be potentially active in the liquid, but there's a whole bunch of stuff not on the surface that's inside the Lego that can't be active in the solution. So odds are the activity coefficient of this Lego is going to be really, really, really small. Likewise, we say that the activity of a solid is essentially 1, same with a liquid. Because the activity goes essentially to the mole fraction as the mole fraction goes to 1. If you have a solid, you have pure, come here. You have pure, looking for a spoon. We'll use the back of this fork. So this solid Lego, come here, is essentially non-active in the solution. Oh my God, this is ridiculous. Whatever. So its activity is going to be represented as 1 because it's essentially pure. Go team. Okay, that's activities. And now I'm going to find my notes that I just put down. So the activity is right here. Going to then now be related to Q and K, and we're going to work within the activities and hopefully have a way to approximate to get them into useful concentrations or pressures. Okay, so Q is, so for this reaction, A, so this is a stoichiometric coefficient times the molecule A plus stoichiometric coefficient molecule B in equilibrium with C, big C, plus D, big D. Okay, and I put a little hat or a little serif thing on my big C's, just so you can tell. Okay, Q equals, we're just gonna go with the big notation first, big pi sub J, A sub J, nu J. All right, what does this mean? Okay, this is a product rule. It's the same as a summation, equals A1 plus A2 plus A3, so on. Whereas big J, or so there's the summation. The big pi equals multiplication. A1 times A2 times A3 times A4, and so on. Okay, so we're just going to multiply these things. and it's raised to the stoichiometric coefficient value J. So what this means is I've got the activity of A to the minus A, because this is the stoichiometric coefficient, and because it's a reactant, it is a subtraction, minus, because we're losing the reactants and we're gaining the products, times A of molecule B raised to the minus B power times AC raised to the plus C power times AD raised to the plus D power. Okay? So this is the notation, the appropriate full notation of what the reaction quotient is. Mathematically, if you see this, that's what it means, but you're familiar with it this way. Anything with a negative exponent means it is in the denominator. And then if it's positive, it is in the numerator. Okay, cool. So those are just the ratio of the activities of the reactants raised to their stoichiometric coefficients divided by the activities of the reactants raised to their stoichiometric coefficients. Go team. Okay, let's give an example. Okay, the example is calcium carbonate. CaCO3 is a solid form, goes into calcium oxide. This is quicklime plus CO2. So this is just lime. That's called quicklime. Cat just made a weird sound. It's concerning. And so the question then is, well, what is the reaction quotient? Well, Q is equal to the activity of calcium oxide times the activity of CO2 divided by the activity of calcium carbonate. But the activities for solids and liquids is equal to 1, which means the calcium carbonate and the calcium oxide are both equal to 1. So 1 times the activity of CO2 divided by 1. Go team! But we also know that the activity of CO2 is equal to the pressure of CO2 divided by the vapor pressure of CO2 pure. So the relationship here, this then means that you've got now the pressure of CO2 divided by the pure pressure of CO2 for the reaction quotient. Go team. All right. And so this is the reaction quotient, but then at equilibrium, K is then P CO2 divided by P star CO2. Cool. All right. And actually, I should note that this is for gases. And so this would be the standard condition CO2 that you would then divide out. And it's really a way of dividing out the units. And you've hopefully seen Atkins do that, where he's got P over P standard. So the way to think about how this works is looking at the, oh my gosh, the cat is causing problems. The way to think about how this works is that the CO2, so if this is your calcium carbonate, it's going to give off CO2, and then you're going to have what's left is going to be this calcium oxide. So the activity of the calcium oxide and the calcium carbonate are going to not be dictating where you are in equilibrium for this reaction, but the amount of CO2 that's present will give you an indication of where equilibrium will lie. And if you think about it, that comes from the idea that the CO2, let me make a couple more. So these CO2s are going to be representative of how much of the calcium carbonate has been active in the solution or in the reaction process. Okay. Okay, so now I'm going to switch gears to go into solutions. So the previous one was gas phase. Now these are going to represent the solutions. So the equilibrium in terms of concentrations, it's going to equal the activity of my lead, or sorry, I've got lead 2 iodide dissociates into lead 2 plus and 2 iodide, and this is in water. So we're going to, so water is our solvent. So I'm going to have the activity of the cation times the activity squared of my ion divided by the activity of the solid lead 2 iodide. And then you're also going to have the activity of water. But in both cases, it's going to be 1, so it doesn't really matter. But it's also going to cancel itself out. Okay, so now we're going to say, well, the activity of lead 2 plus is equal to the activity coefficient of lead 2 plus multiplied by the concentration. And the activity of iodide is going to equal the activity coefficient of iodide multiplied by the concentration of iodide. And so the concentrations then, Kc, equilibrium constant, will be, oh, and also the activity of the solid goes to 1. So you're going to have Pb2 plus multiplied by concentration, multiplied by the activity coefficient, multiplied by the concentration of iodide. And this one will be, I believe, squared. Okay. Now, most of the time, the activity coefficient is going to be pretty large. It's going to be like 0.99 something for things that completely dissociate. And this is where electrolyte chemistry is really, or solution chemistry comes in. And the chemistry is, you have to be considerate of chemical character. And I know I keep saying that, but material science and solution chemistry, like when you got the chemistry of materials, how do you take into account the fact that each of them are different? Well, and there's normally through some sort of empirical relationship. And that empirical relationship comes in with how much does the concentration accurately give us the equilibrium constant. If it accurately gives us the equilibrium constant, those activity coefficients are 1. Yay, moving on. But if they're not, if that doesn't relate to the actual concentration, then something must be slightly off, which tells you that your activity coefficient is not going to be close to 1. There's going to be some that stays in solid phase. So another way to think about this is if this completely dissociates, so your little lead 2 plus and your iodides are all floating around and they're completely surrounded by your water molecules, okay? So they're completely encased within your water molecules, then all of them are active in the solution. Therefore, they should have a very high activity coefficient, or 100% of the concentration of your lead will then be active or part of the equilibrium condition. If that's not the case, if you still have some, lead iodide that's still in its solid form, it's not dissociated. It's not contributing to the equilibrium. It's staying in this solid form here. So it's not as active, which means this number is going to be smaller. And your activity coefficient is going to be 0.98, 0.7, 0.5, who knows? Well, we know from a lot of data that's been collected. But the problem is that you have to know what solvent you're in. So now we're solvent specific and salt specific when it comes to the activities. Cool. Okay. I think that's all I want to talk about in terms of, oh, one more thing. Oh, yes, very important. Okay, so the equilibrium concentration, or the equilibrium constant in terms of concentrations will be equal to this relationship. And let's assume then that the activity coefficients are 1 for iodide and lead, which would make Kc equal to the concentration of our lead 2 plus cation, and our iodide ion squared, whereas both of these are 1. So I'm going to say this is approximately equal to 4 2 plus equals I minus. Okay. So then how do you relate the equilibrium concentration the equilibrium constant in terms of pressures to the equilibrium constant in terms of concentrations. They are not equivalent. There is an additional factor you have to take into account, and that is R times T raised to the delta N, where delta N represents the change in number of gas moles. And so what this does is this says, okay, you've got K sub P is equal to Kc multiplied by RT. And actually, this is the Atkins notation. C standard divided by P standard delta J. Nope. Okay. So this says that you are going to take RT, so this is the thermal energy, and raise it to the number of gas particles that you have changing. So if you have a reaction to where you've got, do I have an example of this? No. So if you have, well, the not this one, but the previous one. So let's see. Okay, sorry, I had to find it. So we had the calcium carbonate goes to, or is in equilibrium with calcium oxide plus CO2 gas. So the Kc relationship here would be the equilibrium constant K is equal to Kc times RT delta N. Well, here you have 1 mole of gas compared to 0 or 0 from your reactant side. So you'd have delta N equals 1 plus 0 minus 0. So here is your, and really it's just from the number of moles of gas. So not gas, so those are both 0. So your delta N is 1. So to go from your Kc value, you would multiply by RT to go to your Kp value. Okay, so let's talk about, and this is the notation that we use. Atkins represents this, signifying that your RT is in units of moles, which means in order to get this in terms of the number of units or the units associated with your equilibrium, you'd have to divide out the pressure units and then multiply by the concentration units. And so that's what these standard C naught and P naught are. But I want to talk about what this means physically, because you can go through examples and figure out what numbers to plug in and what equation to use, but I want you to think about what this means. The equilibrium constant in terms of concentrations is a solution-based equilibrium. Okay, or solution-based equilibrium. Here, Kp, this is a pressure-based equilibrium. So what you're doing is you're multiplying the ratio of the activities by RT raised to the delta N. So this means if you have an increase in the number of gas particles present from going to reactants to products, wherever your equilibrium is defined, you are raising it to a positive number, which means you are multiplying by RT per mole of gas that's created. Think about the per mole work associated with that change in the number of gas molecules. And what does conservation of energy tell us? The work associated with it will have a thermal energy of RT. So unit RT per particle of gas that goes from the concentration phase. Okay. So then the other thing to think about is that you've got, no, I think that's it actually. So to get from the pressure to concentration, you need to take the concentration and multiply it by the thermal energy associated with creation of those particles, gas particles. Cool. Okay. That's all I got for that one. The next one will be, ice tables. Yay.